A buffer is a solution that resists changes in pH when a small amount of either a strong acid, like HCl Hope, or a strong base, like NaOH Black Panther, is added. And also, an acid-base buffer usually consists of a conjugate acid-base pair, where both species are present in significant quantities in that solution. So because of those two things, I usually combine them to create one definition for a buffer. A buffer is therefore a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid, that resists changes in pH when a small amount of strong acid or strong base is added. And so, of course, the best way to visualize this is through an example. Have a 100 ml sample of dilute HCl that has been adjusted to the pH of 5.00. If we add 1 ml more of HCl, the pH decreases, right? It makes sense. We're making it more acidic, and it decreases to 2.00. And if we add 1 ml of a strong base like NaOH, it's going to increase to 12.00. And so as you can see, the pH range is extremely varied when you have an unbuffered solution, right? Now let's take an example of a buffer solution. So we actually have an acetate solution here, which specifically means the weak acid, acetic acid, and its conjugate base, which is the acetate ion. So we have 100 ml of a buffer solution now that is at 5.00 for its pH. We're still going to add the same 1 ml of that strong HCl Hope, but this time when we add 1 ml of HCl, the pH only decreases to 4.98, very small and very slight. And also, when we add 1 ml of NaOH Black Panther, it increases very slightly to 5.02 as well. So as you can see, it's a plus or minus 0.02 increase or decrease with that buffer solution. And pH changes typically fall within a range of approximately plus or minus 1 pH unit. So 1 pH unit is increasing the pH by 1 or decreasing the pH by 1. So for these buffer solutions, for example, at 5.00, the max pH should be 6.00, the smallest pH should be 4.00. And that is the range that we will see for an example of a buffer range, okay? Now, of course, with the unbuffered solution, it went all the way down to 2 and all the way up to 12. So the range is so vast that it's going to be hard for you to be able to do and have really precise measurements if you have such vasting changes in pH. However, the exact pH range can vary depending on the specific buffer system and its concentration. This was an example of an acetate buffer system, and as you can see, it's plus or minus 0.02 here, not plus or minus 1. So the question to answer becomes, well, how does that buffer actually work? We know it has to do with the conjugate acid-base pair, and we know utilizing the acid-base pair, we can withstand changes to pH when you add a strong acid or a strong base. But how does it actually work? And how it works, folks, is through what is called the common ion effect. And the common ion effect is a shift in the position of an ionic equilibrium away from an ion involved in the process or reaction that you're giving, okay? And that's all going to be caused by the addition or presence of that ion. So the best way to explain it is to get into, of course, an example. So we have our weak acid here, acetic acid, or you can just remember acetic acid, Dr. Strange, mixed with water to form H3O plus and the acetate ion. So this is going to be our acetate ion here, okay? So what happens if I then introduce more acetate ion by adding the soluble salt acetate here to my overall reaction? So I'm going to add this soluble salt, and since it's soluble, it's going to disassociate to the acetate ion and Na+. And so now this acetate ion and this Na+ has the ability to contribute to my overall reaction, okay? And when I'm looking at the actual ions that are able to contribute, we know that sodium is going to be spectator, but that CH3COO- is a conjugate base. It's also acetate ion as well. So I'm like, oh, wait a minute. I have acetate ion here. I have acetate ion here. That is what we call a common ion. And so if I add more of a common ion, it's going to have the ability to shift the equilibrium, just like the definition says. It's going to shift the position of the equilibrium away from the ion involved in the process. What does it mean to shift it away? It means it's not going to be producing that particular ion because it's increasing the amount of that ion. Let's think about it. Just by using good old Le Chatelier's principle, I have more of the CH3COO-, I'm going to increase this product. automatically I'm going to have to shift to the left in order to decrease the product of acetate ion and therefore get back to equilibrium. And so because I have to shift left, what does that mean? That means that this is going to decrease. It also means my H3O plus is going to end up decreasing. And it means that my weak acid here is going to be increasing. So the acetate ion here is the common ion. Of course, it's common to both solutions as we see. And adding acetate ions is just like adding buffer to this overall system. And we can call this a buffer system because we have a weak acid and its conjugate base. So if we're adding more base, as you can see, according to the common ion definition, it allows us to shift back to equilibrium by, again, shifting to the left and increasing our weak acid concentration. And this is exactly how buffers work to maintain pH stability. No matter what acid or base is added, it's going to shift to the left or right, increase and decrease the amounts it needs to get back to equilibrium. And we can also go further and talk about the effect of added acetate ion on the dissociation of acetic acid, right? That makes sense. So if you're going to add more of this base and you're going to produce more weak acid, that means, does this dissociate more then? That is the question. So through data, we do have that answer. We have our initial amount of CH3COOH, which is our acetic acid, and then we have what is going to be our percent dissociation after that base is added. So when no base is added, we have 1.3% of dissociation, which makes sense because it is a weak acid, right? And then we do have that dissociation decrease, as you can see here, as we increase the amount of base that's going to be added. So that common ion essentially suppresses the weak acid from dissociating, and it makes sense. Of course, I'm going to suppress this particular weak acid from dissociating because I don't need more of the conjugate base being formed. I'm already adding it in, right? And so this data table is just proving that point. We can also go further and see of a common ion based on pH, okay? So for example, say we have our acetic acid here, which is going to give us a red solution, which has a very low pH. And so that means we're looking at a very acidic solution here, right? That makes sense. It's a weak acid. And then we have our acetate solution here, which is a higher pH, at pH of 8.9, and it is a basic solution. So it's both of these reactions, except they're being represented visually here with colors and pH. Now, what we're going to do is mix these two things together and create the common ion effect. And what we see is, yes, we have an increase in pH. We do have an increase in pH for sure, but the color of the solution is still going to be the same color that we started with our acetic acid. And yes, we did get an increase in pH because we did have to shift. But as you can see, this red color lets me know that I had to produce that weak acid. And I had to produce weak acid because by adding that more and more base, I shifted to the left. And so this is just a very visual representation of that. So a buffer works because the relative concentration of buffer components, usually a weak acid and its conjugate base, are balanced in such a way that they can resist significant changes in pH when an acidic or basic substance is added. And that allows the solution to maintain a stable pH level, right? And we can usually capture the ratio of those buffer components, meaning the weak acid and its conjugate base, using the equilibrium Ka dissociation constant. So we're going to start off with our acetic acid, or acetic acid Dr. Strange. We're going to mix it with water. So we're mixing a weak acid with water. That means we're going to be in equilibrium to form the conjugate base and, of course, H3O plus. So our Ka is going to equal our products divided by our reactants. Our products are our conjugate base and H3O plus divided by our weak acid, because water is a pure liquid, right? So it's going to be 1. And so here we have our equilibrium expression. Now, as we saw before, the H3O plus concentration is very important. If it increases, then we know we're going to have a lower pH. And if it decreases, then we know we're going to have a higher pH. So this is going to give us the ability to figure out exactly the pH, which then is going to prove that the buffer is keeping it within a range, right? So to make it easier to create a relationship between the H3O plus concentration and, of course, the ratio of the buffer components, we then solve for H3O plus. And when we solve for H3O plus, we're going to have our Ka value times our weak acid divided by its conjugate base. Now, as you can see, Ka is going to be constant. A lot of times that's going to be our given value, right? And so the H3O plus concentration is then going to depend on the ratio of the buffer component concentrations that we see here. And so knowing this relationship between H3O plus and the ratio here, knowing that it's a direct relationship or proportional to one another, makes it easier for us to gain information about buffer solutions. So I'm like, okay, if I'm going to add more acid, like that means I'm going to be increasing the products here. It's like saying I have 1,000 divided by 1. So I have way more of my weak acid here. Then automatically I would know that I'm going to increase my H3O plus concentration because it's directly proportional. If I increase my H3O plus concentration, then that means my pH has to lower. And sometimes it will directly be acidic, or other times you'll just say or understand that it's going to lower the pH. Okay? Why would it be lower? Because you have a higher H3O plus concentration. You can do the same thing with when something is more basic. So say I'm going to add more base here. If I add more base, it's like saying I have 1 divided by 1,000 now. I'm adding more of that conjugate base. So my overall ratio is going to be, of course, decreased. Okay, my overall ratio is decreased. If I decrease my ratio, since it's proportional to H3O plus, I'm also going to decrease my H3O plus concentration. If I decrease my H3O plus concentration, that means I'm going to increase my pH because it's going to be more basic, folks. Okay. And so again, sometimes you'll see the pH clearly be basic, or sometimes that slight change will just be increasing. We are talking about a buffer here, right? So we know it shouldn't go higher than 1 pH unit or lower than 1 pH unit. So if I have a base here, it might go as high as 1 pH unit in my buffer range, depending on the buffer system I have, okay? And of course, we want to show this visually. So let's say we're adding and starting with the buffer here. A buffer is going to have equal concentrations of the conjugate base and the weak acid. So as you can see, we have our conjugate base here and this weak acid, they're in equal proportions. Another visual to show this will be this bar graph here, okay? And we still are talking about our acetate buffering system. Now, if we're going to add more acid, which means we're going to add more H3O plus here, then what happens to our overall buffer system? Well, that means the buffer is going to end up having more weak acid. Let's talk about why. If we're going to increase the H3O plus, then that means the conjugate base is going to accept that proton to form more of the weak acid. And so the weak acid concentration is therefore going to increase, but that increase is very slight, as we see here, right? And of course, we can take our buffer component and then we will do the opposite and focus on adding more base, or the OH minus here. When we add more base, this weak acid is then going to donate a proton. And of course, OH minus is going to accept that proton. And when that happens, it's going to form more of its conjugate base here. And you see a slight increase. But because we're dealing with the buffer, and because it has the ability to have that common ion effect and be able to accept and donate protons using this conjugate acid-base pair system, that slight change is not going to affect much when it comes to our calculations, when it comes to us understanding chemical reactions as well, which is pretty cool, right? And here at the bottom, it just shows you the overall reactions. We have our conjugate base accepting more of the acid, forming more of the weak acid here, and of course, water. We have our weak acid, of course, donating a proton to the OH minus, forming water, and of course, its conjugate base here as well. So there's just more ways to kind of show you why those relative concentration of buffer components are important, how we can end up setting up little details to help us remember, and then how we can also see this visually by starting off with the buffer in equal amounts, and then slightly increasing it, increasing the actual acid or increasing its conjugate base, just by knowing that conjugate acid-base pair relationship. So this is why this is pretty cool for you. To go further, remember, these are equal stoichiometric amounts. So it doesn't matter how much of this H3O plus or how much of this OH minus is being used, they are going to be completely used up. Why are they going to be completely used up? Because we want to get rid of them so we can get back to equilibrium, right? So let's think about it. We see arrows this way and we see arrows this way, but in our overall buffering system, it's an equilibrium. Why? Because buffers are going to allow us to use the weak acid or its conjugate base whenever we need. And when we actually get a chance to use them, it actually allows us to use up any additional acid or any additional base to completion. Another reason why this is pretty cool, right? And so maintaining that pH level and figuring out how the buffer works all comes from this understanding. So if you have this down, we'll be able to get and understand buffers as we go along and even apply this as we see in some of our future labs as well, folks. So now I want to talk about the real work. And the real work comes from the calculations that can be related to buffers, right? And beyond that, all the real work it takes to help you understand what happens when you add an acid or add a base. Okay, folks? All right, so you automatically going to start with your buffer solution, right? So you're probably going to be given amounts of reactants. You might be given a round of a product as well, because we're talking about the weak acid and its conjugate base, or the weak base and its conjugate acid. So you'll be given that information, and you will be asked to do a Rice table. This will be your first Rice table, because you want to get your initial amount. You want to be able to get the X value, which is going to give you your ratio of the weak acid to its conjugate base. That's what X value is. So doing that Rice table will allow us to get that X value. And of course, we can go further. Once we get that X value and we get our H3O plus amount, for example, we can go ahead and get our pH. So the initial amount is going to be it's going to be similar to what you're used to already when it comes to equilibrium type problem. All right, folks? Now let's talk about if we were to add an acid or a base. So if we were to add a strong acid, then what's going to happen is the conjugate base of the buffer system is going to basically mix with the H3O plus, or the added acid, to form the weak acid again and water. And this is a complete reaction. That means you're going to completely use up all the H3O plus that was added in general. Okay, folks? Same thing if you add a strong base. You're now going to have your weak acid mixed with OH minus that's added, all the OH minus, because you're going to go to completion, and then you're going to be left with your conjugate base and water. Okay? So when you're adding anything to your buffer system, it goes to completion. And so since I'm adding something to my buffer system, it is going to change the amounts that I start with. And so I'm going to end up having new initial amounts. And those new initial amounts are going to be used in Rice table number 2. So we had our first Rice table to get initial amounts. And then we had to add our OH minus or H3O plus, and that's going to give us new initial amounts. And we have to have another Rice table. So some folks might be saying, how do I get new initial amounts? Well, if I know the amount of like the H3O plus and OH minus, for example, they give me an initial amount of it, and I can use that to find the concentration, or even if they give me a starting concentration of these amounts. Since it's going to be used up completely, whatever I start off initially, it's going to be the amount that's used up, so I can automatically get my equilibrium amount of OH minus and H3O plus. And so in a Rice table, for example, once you have your OH minus, then you would have the equilibrium amount. And so that X value for this Rice table is going to equal the OH minus concentration if you added OH minus, or the H3O plus concentration if you added H3O plus. All right, folks? So the X here was a ratio from your initial amount. The X value here is going to be equal to the equilibrium amount of OH minus and H3O plus. And now that's how you're going to get your new initial amounts for that second Rice table, okay? From that second Rice table. Now when you have your new initial amounts, there is a third Rice table, folks. Yes, you have to do this. So there is a third Rice table with those new amounts after you added H3O plus or OH minus, okay? So when you add more acid, you're going to increase your products, and so you're going to have a larger ratio, as you see here. And of course, we already know you're going to have a smaller pH. And then that means your X value is going to be related to the ratio, and that'll just give you that pH value, okay? And so really, with this third Rice table is giving you the answer to the overall question. And normally, these type of questions are actually for pH, and so that's what you see here. All right, folks? Same thing if you add a strong base, you're going to increase your conjugate base here, making the ratio smaller, and therefore your pH is going to be larger. So it's basically telling us exactly what we're looking for. This is a summary of how you would approach buffer-based questions. Now, you know I'm not going to force you to do Rice table 1, 2, and 3 and go through it. I'm going to give you an example of how to do this, and then I'll show you a quicker way to do it with a new equation that you can use. Okay, folks? So let's go ahead and get to that.